This question is about period 3 elements and their compounds, which is not correct about magnesium hydroxide. So it says it is used to neutralise stomach acid. Well, that is true because magnesium hydroxide is in milk of magnesia and it is able to neutralise acid because it is an alkaline. It forms a solution of pH 14. Well, that's not true because magnesium hydroxide is sparingly soluble, so it has a pH of around 8 to 10 at 25 degrees C. So this is the one that's not true, but we can just double check. It has the empirical formula, and the molecular formula of having 2 hydrogens, 1 magnesium and 2 oxygens. That's true. Give an equation for the reaction of aluminium oxide. So aluminium is a 3 plus ion and oxide is a 2 minus. So the formula of aluminium oxide is Al2O3. Sulfuric acid is H2SO4. So when you react aluminium oxide with an acid, it behaves as a base. Because remember that aluminium oxide is amphoteric. Now when something is a base, it provides the metal ion to the salt, and the acid provides the anion, the negative ion. So sulfuric acid provides sulfates, aluminium oxide provides aluminium ions, and then we have to put those two together. So to balance the 3 plus and the 2 minus, we'd need 2 of the 3 pluses and 3 of the 2 minuses. So that would be our formula of aluminium sulfate. And acid plus base makes salt plus water. Then we'll need to balance our equation with 3 sulfates, and that's why we'll get the 3 waters. Identify a reagent or a test that could be used to distinguish between aqueous solutions of sulfur dioxide and sulfur trioxide. Well, in water, sulfur dioxide reacts to form sulfuric 4 acid, whereas sulfur trioxide forms sulfuric 6 acid. We know from our study of period 3 oxides that sulfuric 4 acid is a weak acid, whereas sulfuric 6 acid is a strong acid. So what we're looking for is something that can tell the difference between a weak and a strong acid. So we could use universal indicator. We could use a pH meter. If we were to use a pH meter, our weak acid would be like pH 3 maybe, and our strong acid would be like pH 1. Here, our weak acid would be an orange colour, and our strong acid would be a red colour. The mass spectrum of the element phosphorus, which if we look in the periodic table is 31.0, so it must have a 31 isotope, has a peak at 124. Now if you do some simple maths on that, you can see that there are 4 31s in 124, and we know that the formula of phosphorus is P4. And then we need to remember, it's asking us the species, and we're talking about in a mass spectrometer where they're ionized, so we need a P4 plus, and then we need to say which isotope it is that would add up, 4 of what would add up to 124, so that's 4 31s. So phosphorus 5 oxide is P4O10, sodium hydroxide is NaOH. So P4O10 plus NaOH. So P4O10 must be acting as our acid and NaOH must be acting as our base. So remember from before that the base provides the metal ions and the acid is going to provide the anion, the negative ion. So the negative ion for P4O10 would be the phosphate ion, the PO43 minus ion. So if I put those together, get Na3PO4 plus water, acid plus base makes salt plus water. Then we need to do a bit of balancing. Now there's 4 phosphoruses, so we'll need to make 4 of these, which is 12 sodium hydroxides. And if we balance it out, we need 6 waters to do that. What happens when P4O10 reacts with water is that we're going to create phosphoric acid, H3PO4. And we although we don't need an equation here, we could balance this equation like this. It's not necessary. We just need to draw the displayed formula. So we need to make sure we do it displayed of H3PO4. Now, a little hint is if you went to the data sheet, you could look up the phosphate, the dihydrogen phosphate ion from the DNA section, and you can see on the data sheet that they kind of draw this in the DNA section. This has got 2 of the H's on, and then it has a minus here. Now, given that we've got all 3 H's on, we're trying to draw it with another OH here. So we've almost got half the answer on the data sheet. What we just need to do is display that. So that's not my answer, that's just some working that I'll cross through before I finish. So we need to show every atom and every bond because it's displayed. You don't need to show the V-shaped bond angle on your oxygens. I just am doing. You could do it without showing that. Could have shown that it's tetrahedral as well because it's got 4 bonding areas, but again, not needed. So I'm just going to cross through my working. These are not my answers, but they helped me come up with my answer. Okay, the last part of the question asks us to explain why the melting point of these substances are so different and to refer to the structure and bonding in each case. So I'm going to start by doing that. So I'm going to say NaCl, which is sodium chloride. It's made of sodium ions and chloride ions, so it is giant ionic, and that's its structure. Its bonding is strong electrostatic forces of attraction between oppositely charged ions. Chlorine, Cl2, is simple molecular because it's small covalent molecule. That's its structure. And we've got it's a non-polar structure, so we've got with weak van der Waals forces between the molecules. Hydrogen chloride, HCl, is also simple molecular, but it's polar. And so, as well as having van der Waals, it also has dipole-dipole forces. Between the molecules. Okay, so why are their boiling points or melting points so different? We need to be clear then that the forces of attraction between oppositely charged ions, ionic bonds, are much stronger than intermolecular forces. Which both van der Waals and dipole-dipole are a type of. So the melting point of NaCl is much higher as more energy is needed to overcome these forces. what we need to look at now is why the melting point of chlorine is higher than that of hydrogen chloride, because our understanding of intermolecular forces is that dipole-dipole forces are stronger than van der Waals, yet this data shows it the other way around. So what we would need to realise is that chlorine, Cl2, has an MR of 35.5 twice, so that's 71. Whereas HCl is a H and a Cl, so 36.5. The MR of chlorine is much greater, and therefore chlorine has more electrons than HCl and has stronger van der Waals between the molecules than the dipole-dipoles are between the HCl molecules. So since Cl2 is a larger molecule than HCl with more electrons, it has stronger van der Waals between its molecules. And then what we can say, looking at the data, is since the melting point of Cl2 is higher than that of HCl, the van der Waals between Cl2 molecules must be stronger than the dipole-dipole forces between HCl molecules.